In this lesson, we're going to be discussing the most important aspect of trigonometry that's going to be following us through the entire semester and everything that we do. It's the most important concept in all of trigonometry that unfortunately many students, having taught calculus 1, 2, 3, differential equations, many students don't really understand this component of trigonometry, and instead they've relied too much on trying to work through what their calculator says instead of understanding the concept. We're going to do our best today to give you a solid foundation in the trigonometric functions so that as you move forward through this class and you move forward into future classes, you're going to really understand what's being said when we say sine, cosine, tangent, and so on. Now let's take a look at this triangle that has actually been drawn on the XY coordinate system. So if this is our x-axis and this is our y-axis, then this point right up here is just going to be some point called xy. And if that's a point called xy, then that must mean that this length down at the bottom is going to be whatever that x coordinate is. And we should realize that this height is going to be whatever the y coordinate is. Now, because this is a right triangle, we refer to this side over here as r. It's the hypotenuse. And we're going to see that it actually is called r because it relates to the radius of a circle eventually as well. But for now, I would just like to come up with a relationship between x, y, and r. Now, obviously, if we're given the point x and y, we don't know what r is. So let's recognize that by the Pythagorean theorem, x squared plus y squared is equal to the radius squared. Now notice when I square x, I get a positive number. When I square y, I get a positive number. When I add these two positive numbers, I get a positive number. So when I take the square root of both sides, we should recognize that r can be found by simply taking the square root of x squared plus y squared. So this shows us a relationship between the three sides of a right triangle. Okay, most importantly, it is a right triangle. Okay, so what we're about to discuss in this lesson are properties of the side lengths of a right triangle in relation to some angle. So notice that that angle is right down here. That angle of rotation is always starting from the positive x-axis and rotating upwards. Okay. So now what we'd like to do is look at this diagram and start to look at all of the different ratios of sides that we could create. Okay, so the various ratios, okay, the various ratios of sides are how many different ways could we compare one side to another side. So one way we could do that is we could start by saying, what is the relationship between y and r? What is y divided by r? How tall is this triangle in comparison to the hypotenuse? Okay, there's other ratios as well. We could say, how big is the base of the triangle compared to the hypotenuse? Or in other words, how long is x compared to r? There's another ratio. We could also say, how big is the height of the triangle compared to the base of the triangle? Notice that every one of these is relating different sides. So we're making a comparison between how big one side is in comparison to another side. So how big is y compared to x? But notice that in addition to this, we could also look at the reciprocals. Instead of saying how big is y in comparison to r, we could say how big is r compared to y. Or how long is r compared to x? Or how long is x compared to y? So notice within any right triangle, we have 6 different ratios that we could set up between two sides. And all we're doing when we're making that comparison is figuring out how big is one compared to the other. So let's take a look at an example then. To understand these 6 ratios a bit better, what I've done is I've looked at this same exact diagram, but now I've drawn the side lengths exactly the size that they are in this triangle, just right underneath each other. So side x up top here is the same exact length as side x, and this vertical length of y is exactly the same as this horizontal, this length here. And r has this length, which is obviously the longest of the 3. So when we're trying to compare the 3 sides, what we're really trying to do here is see how big is one side compared to another. You could think about it in terms of, say, a percent. You could see this in terms of a percent, perhaps. So let's start off with how big is y compared to r, okay? So looking at y over r, okay, y over r is essentially, I mean, if I look at how big is y, this length right here, how big is the blue compared to the orange? Well, if I was to just kind of overlap those and see how big one is compared to the other, it looks like maybe it's about 80% the size. So I'm going to say that y over r is maybe approximately 80%. Now we typically don't write it in terms of percentages, so we would maybe say 0.8. Okay, well, we can take a look as well at a couple of other ratios. So the second ratio it looks like we have is x over r. So now let's move y out of there. And now let's compare x with r. Okay, so if I look at how big x is compared to r, it looks like it's less than 8, maybe about 2/3, maybe about 60% or so. So I'm going to see down here then that x over r is approximately 60% or so. But we typically don't write them in terms of percentages, we write them as decimals. So I would write this as maybe 0.8. Okay. And the next one it looks like we have is y over x. So if we want to compare y to x and say how big is y compared to x? Okay. Well, now we have to compare y to x. Now this one's a little trickier because notice y is larger than x. So if we say how big is y compared to x, it's definitely more than 100%. Y compared to x will definitely be bigger than 1 because y is bigger than x. So now we just have to figure out how big is this difference right here, that little difference, compared to the original. Right? It looks like it's maybe about 1/3 more, somewhere about, I don't know, 33% more. So it looks like y over x would be somewhere approximately, I should make sure to use the approximate, okay? It looks like y over x gives an amount that's approximately 100 and we're just gonna say 33% the size, okay? But notice we typically don't write it as a percent, so instead we would write this as 1.33. So we can already see, hopefully, that the ratios that we're trying to create for this triangle is nothing more than just saying, given this triangle, how big is one side compared to another side, okay? And so by lining them up horizontally, we can maybe see a little bit better how big one side is compared to another. But we're eventually not going to have to worry about that because we're going to know what the side lengths are. And if we know the side lengths, we really just have to divide the two and see what the ratio is. Okay. Well, let's go ahead and continue to find a few more here. Let's go ahead and compare R to Y. Okay, so let's find the ratio of R to Y. Okay, well, notice R is the orange one, Y is the blue one. So why don't we go ahead and compare R to Y? I'm trying to line these up so the left sides are the same, but it's a little hard to do so. That's good enough. Okay, so now if we try to determine how big is R compared to Y, then this would be a little bit trickier to do, again, because I see that R over Y is definitely more than 100%. So it's 100 and something. If R is larger, if the numerator is larger than the denominator, it's bigger than 100%. So now we just want to see how big is this extra compared to here. Now it looks like it's less than a third. Maybe it's a fourth, maybe it's a fifth. I'm going to say it's maybe about 120% or so. This is all right now just an approximation. So we're going to say that this is approximately 120%. So because R is bigger than Y, we see that this is 120%, so 1.2. So you can see that each of these ratios is giving me a different amount or a different number, a different value, okay? If we look at the other, the reciprocal, we could see how big is R compared to X, okay? Well, now that means we can compare the orange one to the black one, okay? And if we compare those, then again, you could see that R over X is going to be something more than 100%. So R over X is approximately 100 and something, okay? But if I was to look at R over X, then I would say, how big is this amount, okay, in comparison to here? All right, so it's 100 and something. It looks like it's, I don't know, approximately 2/3 of the way. So maybe we look at it and say it's 2/3. Okay, so we could say that 2/3 of one is 67%. So it looks like maybe approximately 167% the size, which we're not going to write as a percent. We're going to write it as a decimal and say 1.67. There's only one last ratio that we could possibly find, and that's the ratio of X compared to Y. So now that means that we're going to move X around. We're going to compare X to Y. How big is X compared to Y? Well, again, X is less than Y, so it's a certain percentage of it. So I mean, if we were to, again, it's how big is this piece right here. So it looks like if we, I don't know, make that whole amount, it looks like it's approximately 75%. Okay, so the black one is approximately 75% of the blue one. So we're going to see that X compared to Y is approximately 75%. Okay. 75%, or in other words, 0.75. All right, so what we have done here is we've just manipulated the base, the height, and the hypotenuse, lined them up to where we could actually see how big one is compared to another. And now we just made the comparison about how big those ratios are. Now, don't get scared about this when I tell you that each one of these 6 ratios have a particular name. Each of these ratios have a name here, and let's go ahead and start writing their name. So this is all based off of this angle. So the fact that this is the angle that formed this particular triangle See how that angle pointed directly to this point up here? Okay, so at that particular angle, this is the triangle that's drawn. Every different angle that you rotate through will have a different triangle. And so basically what this is referred to as, this ratio, has a name. It's called sine. And we know that this ratio has a name. Its name is cosine. And we give this ratio a name, the height compared to the base. Its name is tangent. Many of you have probably heard these phrases before, but never really thought about what they actually are referring to. They're simply names of various ratios in a triangle. So notice that this one over here, r compared to y, has a name of cosecant. While r compared to x, or in other words, how big is the hypotenuse compared to the base, that's called secant. And finally, this last ratio, x over y, how big is the base compared to the height, that has a name as well. It's simply called cotangent. So there are 6 different ratios within a triangle, and that's why we refer to them as trigonometric functions, because what we are referring to here is by their shorthand notation, and I'll write out what their shorthand notation is here. If I ask you, what is sine of theta? Then that's simply telling me if I draw the angle theta, how big is the height compared to the hypotenuse? That's what we mean by sine theta. If I say, what is cosine theta? Notice that this is a function. It's a function of theta. As theta changes, my ratio changes. So this is saying, as theta changes, what is my base compared to my hypotenuse? While over here, the shorthand notation is tan theta. Every one of the ratios has a 3-letter symbol for what its name is. Cosecant has the 3-letter symbol of CSC. So we say cosecant of theta. And if I ask for cosecant of theta, that means when you draw the angle theta, what is the hypotenuse compared to the height? Secant is SEC, secant of theta. How big is the hypotenuse compared to the base? And lastly, cotangent has a symbol COT. So when we say cotangent of theta, we're saying how big is the base compared to the height. So why don't we now put actual values on each of these side lengths, okay? So let's just say that x is going to be 3 units long. And it looks like y is a little bit bigger. So let's say that that's 4 units long. And the orange is a little bit bigger. So we'll say that that's 5 units long. So that would mean if we get rid of these side lengths within our triangle, that would simply mean that we have a base of 3, a height of 4, and a hypotenuse of 5. So now with this information, we're going to be able to answer these questions in a bit more detail. Now I'm going to leave these percentages up here that we ended up coming up with in our last diagram, because we're pretty confident that these are, I realized I made a mistake on this. It's not 0.6, it's 8, it's 0.6 obviously, okay? So notice that, that we referred to y over r, okay, as sine of theta. Sine of theta, by definition, is y over r. So it means that sine of theta is simply going to be the value of 4 over the value of 5. And in general, we often write our trigonometric functions as fractions. So this answer is 4/5. But I'd like you to think about what 4/5 is as a decimal. It's 0.8. It's 80%. The reason it's 80% is simply because of the fact that 4 is 80% of 5. Sine of theta is 0.8 because the 4 is 80% of the size of 5. So when we take a look at cosine of theta, okay, cosine of theta by definition is x over r. So if x is 3 and r is 5, then cosine of theta is 3 over 5, which as a decimal is 0.6, which is approximately what we recognized when we made the comparison of their side lengths. So now let's look at tangent of theta. Tangent of theta, by definition, is y over x. Y we just determined was 4. X we determined was 3. So we know the tangent of theta is 4 over 3. Now notice 4 is bigger than 3, so this answer will be bigger than 1. So this is actually 1 1/3, which is the same as 1.33. So each of these function values that we're getting for our trigonometric functions are literally just ratios of two sides. And it's our job in trigonometry to memorize this, to know this, and to understand that each of these ratios that have these really peculiar names, sine, cosine, tangent, and so on, are nothing more than particular ratios of sides. So cosecant of theta is r over y. Well, if r is 5 and y is 4, then I know that 5 over 4 is bigger than 1. This is 1 1/4, which is 1.25. Okay, so we were a little bit off, but it turns out that we were pretty darn close based off of what the proportion was, right? If we take a look at secant of theta, okay, we can take a look at secant of theta and see that by definition, secant of theta is the reciprocal of cosine, or in other words, r over x, and therefore secant of theta is simply 5 over 3. Again, 5 is bigger than 3, so this ratio is bigger than 1. So secant of theta is 1 2/3, which again is 1.67. And finally, we've got cotangent of theta. If I take cotangent of theta, by definition, that's x over y. And cotangent of theta is then the x coordinate of 3 over the y coordinate of 4. And sure enough, by looking back to our horizontal lines right up here, we can see why that would be true. That cotangent is nothing more than just how big is x compared to y. It's 3/4 the size, and therefore that's how big cotangent of theta is going to be. Now the beauty of this relationship, which I highly suggest, when it comes to the terminology, when it comes to memorizing these 6 trigonometric ratios and what their ratio actually is, flashcards can be very helpful for you to be able to memorize and know these right off the bat. You should be able to look at a triangle and say, what is cotangent theta? That's x over y. Cosine of theta? That's x over r. And be able to recognize what those ratios actually are. But the beauty of this is that if we're given this point, okay, if we know that we have some x and y point, which up here is the point 3, 4, the x and y point doesn't need to be in quadrant 1. We could have a problem where the x and y point is in some other quadrant, maybe quadrant 3, and we could redo this problem. And we would just have to recognize at that point that each of the 6 trigonometric function values may be negative because x and y could be negative. And so why don't we go ahead and take a look at an example of that. Let's say we want to find the 6 trigonometric functions of theta if the terminal side of theta passes through the point -3, -4. So we first of all draw our diagram. We can obviously see that this is going to be in the third quadrant where the point is -3, -4. And we can see that our x coordinate is -3, our y coordinate is -4. So now we want to find our r coordinate. Now remember that r is found by simply taking the square root of x squared plus y squared. And in this case, we know what x and y are. We know that x is -3, and we know that y is -4. So we're simply taking the square root of 9 plus 16, but that's just 25. Now notice that most square roots are not going to simplify nicely to an integer value, but this one does. Turns out that r is in fact equal to 5. So we kind of come over here and recognize that if r is equal to 5, then that described the value of the hypotenuse. And with that said, we can now find our 6 trigonometric function values. We know that sine of theta is y over r. And cosine theta is x over r. And tangent theta is y over x. Now, once we know these three, the final three are relatively simple because they are just the reciprocals of these. And so the other three are cosecant theta, which is r over y. We could see secant theta is r over x. And finally, cotangent theta is x over y. And so by looking at each of these individual ratios, we're just looking at the triangle itself and recognizing what x, y, and r represent. Noticing that some of these values will be negative. So if I take a look at y over r, notice that this result is -4 over 5. So notice that it's not saying that the y value is -80% of the r value in this instance anymore. What it's just saying is that when you look at the triangle itself, how big is one side compared to another? But when you look in different quadrants, the signs of each of these ratios may be different. And so when we take a look at y over r, we get -4/5. X over r is -3/5. And finally, y over x is -4 over -3, which we need to recognize is back to positive again. And now to take the reciprocal of each of these, we just simply get -5/4. R over x would be -5/3. And notice again, we're not saying that the r value is negative. It's just a negative fraction at this point. So it's 5 over -3 or -5/3. And lastly, x over y is -3 over -4. But again, a negative divided by a negative turns right back into a positive. So when we represent each of the trigonometric function values, they're simply fractions, which could be written as decimals if you were to use your calculator, but we want to keep them as fractions to make them exact if possible. And whenever we do so, we realize that there's certain situations where the trigonometric function values will be positive or negative depending on what quadrant we're in. We should note that the r value is always the directed distance from the origin out to the point. And so the r value should always be positive regardless. But it's only the x and the y values that could potentially be negative at certain locations. So I'd like to extend this idea, knowing what the definitions of our 6 trigonometric functions are, to finding the trigonometric function values of the quadrantal angles. So we're going to take a look at each of these locations here. And since any point along a particular angle, and now when I write 90 degrees, obviously at the top of the y-axis here, what that's referring to is that this is 90 degrees. And when I write 180 degrees on the left, I'm referring to the fact that this is 180 degrees, or that this is 270 degrees. So it's just a way so we don't clutter up our graph, we just write it on the outside. Now, we could pick any point along these angles. And so the easiest point that we would typically choose would be the point that's 1 unit away from the origin. So if I were to pick this to be the point 1, 0, then we should realize that at each of our locations, in this case, x is equal to 1 and y is equal to 0. And over here, we would see that x is equal to 0, but y is equal to 1. Now remember, we could also have negative x and y values. So back here, x is negative 1 and y is equal to 0. And finally down here, we see that x is equal to 0 again, but y is equal to negative 1. Now remember that the radius, or the r value, is always 1 unit away, or is always a certain amount away from the origin. And so every one of these points is simply 1 unit away. So for all of these, the r value would be 1. And since x, y, and r are the only values that we need in order to find our trigonometric function values, this is really the diagram that we need to think about when we're trying to find the trigonometric values of quadrantal angles. We don't have to memorize this, we just visualize where we are. So let's talk about maybe the trigonometric function values of 180 degrees. So keeping in mind the definitions of each of these, notice that r is going to be 1 in every one of these. So if the denominator is ever r, we're just simply dividing by 1. So this would be 0 over 1, which is 0. So sine of 180 degrees is 0 because the length of y compared to the length of the r value is obviously 0 since there is no y coordinate. But if we were looking at the ratio between the x coordinate and r, that becomes negative 1 over 1, which gives me an answer of negative 1. And lastly, if we look at y over x, notice that y is 0 over x, which is negative 1. So when we compare y to anything, I know that the answer is simply 0 because of the fact that there is no y coordinate. It didn't raise at all. But now we look at the reciprocal of these and realize the cosecant of 180 is r over y, which is 1 over 0. And now we realize that there's some times at the quadrantal angles where we get an undefined value. Obviously, if x, y, or r is 0, then we know that we could be dividing by 0. But r can never be 0 since it's a distance away from the origin. And so notice that the only values that are possibly 0 are r or x. Now again, we have 1 over x, which is negative 1, which means that secant of 180 degrees is negative 1. And finally, cotangent of 180 is 0 over, I'm sorry, that's wrong. X is negative 1, so it's negative 1 over 0. And because y is 0 again, we know that we're going to be undefined here as well. So we can see there were two function values that gave undefined. It was cosecant and cotangent. And that's simply because of the fact that we were dividing by 0 in both of those circumstances. Well, notice at 180 and at 0, y is 0. So those are sometimes going to be undefined if we're looking at those locations. On the other hand, if we were looking at 90, now we could 90 or 270, we could see that x is 0 in this circumstance, which means we look to the places where x is 0, and that would tell us that secant and tangent would be undefined in those circumstances. So even though we couldn't draw a triangle for the quadrantal angles, it didn't mean that we still weren't able to find the ratios of the x, y, and r values in order to still find values for those trigonometric functions.